Welcome back to the glass plate. In the previous example, we discussed how a layer of salt can be removed from a pipe by flowing fresh water through the pipe in which the salt dissolved. We set up our balances to find out what the concentration along the tube is, and we found that this mass transfer into the fluid is governed by a mass transfer coefficient which was about 10 to the minus 5 meter per second. Moreover, we found that the concentration profile is developing along the tube, starting from fresh water, and more salt is carried away, so the further into the pipe, the more downstream, the higher the concentration. But we also saw from our analysis that if you take the first 10 meters, the concentration here is 0. 10 meters away, the concentration of salt in the bulk is only up to 4 kilogram per cubic meter. Still far away from the equilibrium 50, which is here sitting at the boundary of that salt layer, and which is the driving force, that 50 towards the bulk, for the entire process. Now we're going to try and equate how fast is this layer dissolving, how long do I need to flush. And we're going to do that for the first part of the pipe, assuming that our pipe is 10, max 20 meters long. And thus I'm going to use that the driving force delta C for mass transfer, which is by definition C star here, the concentration close to the layer, minus C at position X, is by and large C star minus 0. This is still low for the first 10-20 meters, so it's going to be close to C star itself, a constant. To find out how fast this layer is dissolving, I need now to set up a balance that deals with the layer itself. In the previous example, we dealt with a mass balance for the salt in the liquid, but now our control volume is a part of that layer, and out of that, sure, stuff, salt, is disappearing. So I'm going to make a mass balance now for the salt layer, and if I set that up, the DDT equaling in minus out plus production, I have now a different type of differential equation, because sure, there's no salt produced. There is no salt coming in. It's about this layer. There's only outflow. And I do know that this outflow is K times the area over which the mass transfer is going, times the driving force, which I estimate, take as a constant C star. I ignore that there is some salt in, as discussed. But it's in this part where it's changing. This is no longer a steady state, because that salt layer is shrinking. So I need to put in here the mass of the salt in that layer, and that is the area times the thickness, and I call the thickness delta, times a density, because it's just a volume of the salt. This is a constant, and you see the density. You see, if we look at what is still changing, it's only the delta that is changing. The thickness of the layer, yeah, obvious, we are trying to flush that salt out, so it's dissolving. So this gives me an equation, differential equation, for the thickness of the layer, which is surprisingly simple. The DDT of the thickness, so how it is changing, shrinking in this case, is minus K, the A's drop out, C star is left over from the driving force, divided by the density of the solid material here. So this is the solids. On this side there are only constants. So this is a linear decaying, and I can easily equate that. Delta as a function of T is the initial delta minus K C star over density times T. And obviously this stops as soon as there is no salt to dissolve and the pipe is clean. So to find out, let me move over to the other side. To find out what that means, let's take that this is roughly 1 millimeter. We didn't want our layer to be too thick because the pipe is clogging. And we would like to know at what time is this a 0. Not the time, but of course the thickness. So if I equate that, then I get on this side delta 0 multiplied by the density of the solid divided by K divided by C star equals the time, I call that tau, that I'm looking for. I just move this to the other side and solve for the time that I call the dissolution time, tau. And this is a nasty surprise. Let's put in some numbers. We had this 10 to the minus 3 meters. Density of salts, easily that of water, so let's put it at 2000, 10 to the power plus 3. This one we already had, 5, 10 to the minus 5, and this was 5 times 10 to the power 1. So this is roughly 25 for this, 2 over 25 is roughly another 10 to the minus 1, so I have 10 to the minus 3. 2 and the 5s and the 5, 10 to the minus 1. 10 to the power 3 for this density, and here 10 to the 1 from C, and 10 to the minus 5 from the K coefficient, the transfer coefficient. So if I solve for all these powers, that is out, that is 4, this is roughly 10 to the power 3 seconds, which is a good 15 minutes. So it takes a while flushing. And now 15 minutes may not be long, but compute for yourself how much water you have used. You flush with a meter a second. This is quite a bucket. And it's due to the slowness of diffusion processes, that K here is low because the diffusion is so low, no matter what you try. We kept to keep the driving force at its maximum. We estimated at its maximum. So in practice it will even be slower than this. This concludes our example on how to clean a pipe. Good luck with trying it yourself.